Hi everyone, and welcome back to the wonderful world of calculus. We are still in our section on derivative formulas. In the previous video, we've introduced the concept of derivative function. In order to find the derivative function associated to f of x, we had the choice between a first limit definition, f prime at x equals the limit as b goes towards x, of the change in y, f of b minus f of x, over the change in x, b minus x. Or we had this second alternative definition, which involved doing the limit as h goes to 0, where h represents the change in x, f of x plus h minus f of x. The derivative function enables us to find a recipe that we can then use to evaluate a function's derivative at a variety of points in its domain without having to recalculate limits for every single one of these points. For example, we saw that for any function of the form x to the power n, so for any powers of x, then the derivative rule was n times x to the n minus 1. Again, this is what we call the power rule. Perhaps we can do this kind of operation for other types of functions than those that are simply powers. Let's start with the derivative of a constant function. If f of x is equal to k, so if a function's value remains equal to k for any x, then using the limit definition, f at b and f at x are both equal to k. This is a constant after all. K minus k becomes 0, and 0 divided by any divider becomes 0. The limit of a constant, in this case 0, stays 0. Now perhaps some of you will think that we encountered a 0 over 0 form along the way. Turns out that we haven't, because actually the quotient 0 over b minus x was equal to 0 before we even get a chance to do direct substitution. It's not the limit that is creating the 0 over 0 form. We have a 0 outcome before we even get to that stage. This makes sense. A function that is constant has a slope of 0. Okay, so here's a first rule to add to the power rule that we already have. So the derivative of k is 0, or k prime is 0. There are three functions, or three categories of functions, for which finding the derivative formulas require a little bit more work. The limit definition, f of b minus f of x over b minus x, as b heads towards x, actually turns out to be very difficult to use for these three. So surprisingly and exceptionally, I would say, we're going to use the alternative definition for trigs and exponential functions, and we'll see how that could be a little bit more useful. So starting with the function a to the x. If we could find a general rule, then great. So I'm going to start with the definition f at x plus h minus f of x over h, and let h go to 0. F at x plus h is a to the x plus h. X plus h has replaced x in the general formula. F at x is defined as a to the x. So here's where we stand. If we try direct substitution, we will get a 0 over 0 form. Luckily, exponent properties allow us to break up a to the x plus h as a to the x times a to the h, which highlights a common factor of a to the x. Now, keep in mind this limit takes place on h going to 0. So essentially, h is the variable. A to the x plays the role of a constant then, and can be withdrawn from the limit. And you will notice that the remaining limit is a special form. It's a 0 over 0 form, but of special type that we know equals ln of a. So we found a general rule for differentiating exponential functions. The derivative of a to the x is a to the x times ln of a. without having to do any new work, we can also assume that these steps would apply just as well to a base e exponential. This time, however, instead of stating that the derivative function for e to the x is e to the x ln of e, we can simply say e to the x would be the derivative rule. Okay, so for exponential functions, the derivatives are a to the x ln of a, and in the special case where a is equal to the natural number e, then e of x prime equals e of x. Let's differentiate sine of x. Again, I'm going to refer to or start with the second definition of the limit, the second limit definition of the derivative. Replacing x by x plus h to get f at x plus h, and f of x being sine of x, here is the limit we have to deal with. As h goes to 0, unfortunately, this is a 0 over 0 form, and unfortunately as well, this does not fit the rules of the special limits we have. For those of you who had seen this in high school, then perhaps you're comforted to know that we do trig identities for a good reason. Perhaps you remember sine of a plus b as being a property or an identity, and that's exactly what we're going to use here. The identity for the sine of a plus b, so the sum of two angles, is sine of a cos of b plus sine of b cos of a. So in red, I've highlighted the original form, sine of x plus h, and what the identity allows me to turn it into, sine of x cos of h plus sine of h cos of x. Now we're going to reassemble these terms in a slightly different order. I've regrouped all the terms that have a common sine of x together. So that would be, if I bring you back to the previous slide, that would be the first term in the numerator and the last term in the numerator. So I've juggled these terms around, regrouped them as a first fraction, and the term that did not have a sine of x, but rather a cos of x, I've written in a separate fraction. Limit laws allow us to apply limits to a sum of terms. So I've applied the limit as h goes to 0 to the first and second fractions individually. Just as before, you have to keep in mind h is the variable involved in these limits, and anything that does not include h's are considered constants. So sine of x, which is common to the two terms in the first fraction, is factorable, and in fact it can even be withdrawn from the limit, just like cos of x can be withdrawn from the second limit because it is not dependent on the value of h. So we can factor out sine of x and cos of x, and what we're leaving behind are two formidable limit properties, or two special limits, whose values are, in the first case, 0 for the limit on the cosine term, and 1 for the limit on the sine of h over h term. So sine of x times 0 plus cos of x times 1, and here is our rule. So what we have just demonstrated is that the derivative of a sine function is equal to a cosine function. Basically, if you want to calculate the slope of a sine function, what you need to do is calculate the cosine function's value at that same point. We're obviously going to do plenty of examples in class to reinforce this statement. Here's our last derivative for this presentation. So we're going to differentiate f of x equals cos of x. So second limit definition of the derivative, which we use for exponentials and trigs. So if f calculated at x plus h is applied to the cosine function, we'll have cos of x plus h minus f of x is cos of x. So that's our delta y. At the bottom, the change in x is h, and we're making that go to 0. Direct substitution, replacing h by 0, would give you cos of x minus cos of x. So that's a 0 over h is going to 0 at the bottom, so 0 over 0 form. And once again, this is not a recognizable special limit. However, thank goodness for high school, cos of a plus b is something that has an identity attached to it. Actually, the identity for cos of a plus b is cos of a, cos of b minus sine of a, sine of b, which I am applying to the cos of x plus h expression. So cos of x, cos of h, minus sine of h, sine of x, and minus cosine of x that was there in the first place. As we did for the sine function, we'll regroup these terms a little bit differently. Notice how the first term at the numerator and the last term have common cos x's. So here, we've re-scrambled the terms a little bit, and the cos x terms are regrouped as a first fraction. Those that involve sine of x are placed in a second fraction. Limit laws allow us to split the limits on each of these individual fractions. And you've guessed it, cos of x is a common term to the first limit. And because it does not involve a dependency on h, cos of x is treated as a constant and can be withdrawn from the limit. In the second limit, sine of x is not dependent on h and can also be withdrawn. So extracting those two constants, we are leaving our recognizable limit laws behind, or our recognizable special limits. The first of which goes to 0, the second goes towards 1. This time cos of x is multiplied with 0, and minus sine of x is multiplied with 1. And here is our outcome. We've shown that the derivative of a cosine function is obtained from the minus sine of x function. In other words, if you want to find the slope of a cosine function, you will need to evaluate minus sine at that same coordinate point, or at that same x coordinate. So here's a summary of all the derivative formulas we have up to now. The derivative of a constant is 0, which we proved in this video. The derivative of a power, so x to the n, which was shown in our previous video, is n times x to the n minus 1. The derivative of exponential functions, a to the x ln of a and e to the x. Derivative of sine of x is cos of x, and the derivative formula for cos of x is minus sine of